Hello and welcome to my video on indirect proofs. I'm going to try to go through this as best I can. It's kind of a tricky subject to teach via video, but I'm going to do the best I can, and hopefully this gives you a little piece of information or a little bit of knowledge on how to do indirect proofs. Basically, indirect proofs are used when you're trying to prove something that's almost super obvious, that it's actually really difficult to prove them in a traditional sense. So what we do is we first start by what we're trying to prove is false. So what we're trying to prove is this triangle being equiangular. So if it's equilateral, then it's equiangular. We're going to temporarily assume I may have spelled temporarily wrong. My spelling is, as you guys know, not the best. Temporarily assume that triangle PQR is not equiangular. Okay, so you're going to assume what you're trying to prove is false, or the opposite. Okay, it's not equiangular. So what that means is that there has to be one of those three angles that's larger than another angle. What we're trying to do is we're trying to reach a contradiction. We're trying to contradict the given. So this is the given right here. We want to contradict that. So, all right. So this means there exists one angle, we'll just call it angle P, that is larger than another angle. We'll call it angle Q. Okay, so since the measure of angle P is greater than the measure of angle Q, then the side opposite, so RQ, has to be greater than RP. This is theorem 510 or 511. I forgot the exact number. One of those two theorems. In a triangle, if one angle is larger than another angle, then the side opposite is larger than the side opposite of the smaller angle. Okay, but it says that in our given that PRQ is equilateral. So this is a contradiction, so it can't be true. And that's what we're looking for. This contradicts triangle PRQ being equilateral. Therefore, PQR cannot be equiangular. It has to be, or cannot not be equiangular. Therefore, it has to be equiangular. So these little dots here mean therefore. Therefore, PRQ must be equiangular because it can't not be equiangular. All right, and there's the first one. Okay, the next one here, given the measure of angle, this is either 510 or 511. I always get the two mixed up. One of them's a theorem and the other is the converse. I always get it mixed up. Angle D is larger than angle E. Prove that EF is greater than DF. Okay, so again, the larger the angle is, the larger the side length is. So we're going to temporarily assume that EF, so this one actually has three cases. So EF could be greater than DF, EF could be less than DF, or EF could be equal to DF. So only three cases. What we're going to do is we're going to show that this and this cannot happen. If those two things cannot happen, then what we want to happen happens. So temporarily assume that we'll say EF is equal to DF. All right, if EF equals DF, I'm going to mark that on my triangle. EF equals DF. Then triangle DEF is isosceles with base angles D congruent to E. Okay, but it says um, that D is greater than E. So D can't be equal to E because D is supposed to be greater than E. This contradicts the measure of angle D being greater than the measure of angle E. Okay, so we just proved that this cannot happen there. That's impossible. All right, now let's temporarily assume, so this one we have to do twice, that EF is smaller than DF. Okay, well, if EF is smaller than DF, so EF is right here. If that's smaller than that here, then D has to be smaller than E. And that's 510. So this is 511. Okay, but it says D is supposed to be greater than E. But this contradicts the measure of angle D being greater than the measure of angle E. Therefore, we just showed that this cannot happen. So EF must be greater than DF. And that is your indirect proof. So we're just kind of using process of elimination. And then here's one more. All right, so this is the converse of the hinge theorem. So again, we have three cases here for the measure of angle B and the measure of angle E. You could have the measure of angle B being greater than the measure of angle E, which is what we're trying to prove. You could have the measure of angle B being smaller than the measure of angle E, or you could have the measure of angle B being equal to the measure of angle E. I want to show that those two things cannot happen, and then what I want to happen actually happens because of process of elimination. Okay, so let's temporarily assume that the measure of angle B is equal to the measure of angle E. Okay, so if these two are equal, all right, well that makes the two triangles congruent by side angle side. Triangle ABC is congruent to triangle DEF by side angle side. And then CPCTC says AC is equal to DF. AC is equal to DF. This contradicts the given that AC is greater than DF. Okay, so we know now that the two angles cannot be equal to each other. All right, so let's try B being smaller than E. Temporarily assume that the measure of angle B is less than the measure of angle E. Okay, so B is smaller than E. That makes AC smaller than DF by the hinge theorem. Okay, but this also contradicts this here. AC is supposed to be greater than DF. Okay, so I just showed that that can't be true. Okay, so the only thing that's left is B has to be greater than E. And that is your last indirect proof that I have for you guys. We're going to be using this technique throughout the year, but I just want to show you guys a video in case it didn't make sense earlier on. Basically, you kind of just use process of elimination. Thank you guys for tuning in. Let me know if you guys have any questions on this, as it is kind of a tricky subject.